Chapter 12. Electricity. Electricity has an important place in modern society. It is a controllable and convenient form of energy for a variety of uses in homes, schools, hospitals, industries, and so on. What constitutes electricity? How does it flow in an electric circuit? What are the factors that control or regulate the current through an electric circuit? In this chapter, we shall attempt to answer such questions. We shall also discuss the heating effect of electric current and its applications. 12.1 Electric current and circuit. We are familiar with air current and water current. We know that flowing water constitute water current in rivers. Similarly, if the electric charge flows through a conductor, for example, through a metallic wire, we say that there is an electric current in the conductor. In a torch, we know that the cells or a battery, when placed in proper order, provide flow of charges or an electric current through the torch bulb to glow. We have also seen that the torch gives light only when its switch is on. What does a switch do? A switch makes a conducting link between the cell and the bulb. A continuous and closed path of an electric current is called an electric circuit. Now, if the circuit is broken anywhere or the switch of the torch is turned off, the current stops flowing and the bulb does not glow. How do we express electric current? Electric current is expressed by the amount of charge flowing through a particular area in unit time. In other words, it is the rate of flow of electric charges. In circuits using metallic wires, electrons constitute the flow of charges. However, electrons were not known at the time when the phenomenon of electricity was first observed. So, electric current was considered to be the flow of positive charges, and the direction of flow of positive charges was taken to be the direction of electric current. Conventionally, in an electric circuit, the direction of electric current is taken as opposite to the direction of the flow of electrons, which are negative charges. If a net charge Q flows across any cross-section of a conductor in time t, then the current I through the cross-section is. The SI unit of electric charge is coulomb, C, which is equivalent to the charge contained in nearly 6 times 1018 electrons. We know that an electron possesses a negative charge of 1.6 times 10 to 19 C. The electric current is expressed by a unit called ampere, A, named after the French scientist André Marie Ampère, 1775-1836. 1 ampere is constituted by the flow of 1 coulomb of charge per second, that is 1 A equals 1 C, 1 S. Small quantities of current are expressed in milliampere, 1 milliampere equals 10 to 3 or in microampere, 1 microampere equals 10 to 6. An instrument called ammeter measures electric current in a circuit. It is always connected in series in a circuit through which the current is to be measured. Figure 12.1 shows the schematic diagram of a typical electric circuit comprising a cell, an electric bulb, an ammeter, and a plug key. Note that the electric current flows in the circuit from the positive terminal of the cell to the negative terminal of the cell through the bulb and ammeter. Figure 12.1 a schematic diagram of an electric circuit comprising cell, electric bulb, ammeter, and plug key. Example 12.1. A current of 0.5 A is drawn by a filament of an electric bulb for 10 minutes. Find the amount of electric charge that flows through the circuit. Solution. We are given I equals 0.5 A, T equals 10 minutes equals 600 S. From EQ. 12.1 we have Q equals it. Equals 0.5 times 600 S. Equals 300 C. Questions. 1. What does an electric circuit mean? 2. Define the unit of current. 3. Calculate the number of electrons constituting 1 coulomb of charge. More to know. Flow of charges inside a wire. How does a metal conduct electricity? You would think that a low-energy electron would have great difficulty passing through a solid conductor. Inside the solid, the atoms are packed together with very little spacing between them. But it turns out that the electrons are able to travel through a perfect solid crystal smoothly and easily, almost as if they were in a vacuum. The motion of electrons in a conductor, however, is very different from that of charges in empty space. When a steady current flows through a conductor, the electrons in it move with a certain average drift speed. One can calculate this drift speed of electrons for a typical copper wire carrying a small current, and it is found to be actually very small, of the order of 1 mm S1. How is it then that an electric bulb lights up as soon as we turn the switch on? It cannot be that a current starts only when an electron from one terminal of the electric supply physically reaches the other terminal through the bulb, because the physical drift of electrons in the conducting wires is a very slow process. The exact mechanism of the current flow, which takes place with a speed close to the speed of light, is fascinating, but it is beyond the scope of this book. Do you feel like probing this question at an advanced level? 12.2 Electric potential and potential difference. What makes the electric charge to flow? Let us consider the analogy of flow of water. Charges do not flow in a copper wire by themselves, just as water in a perfectly horizontal tube does not flow. If one end of the tube is connected to a tank of water kept at a high level, such that there is a pressure difference between the two ends of the tube, water flows out of the other end of the tube. For flow of charges in a conducting metallic wire, the gravity, of course, has no role to play. The electrons move only if there is a difference of electric pressure, called the potential difference, along the conductor. This difference of potential may be produced by a battery consisting of one or more electric cells. The chemical action within a cell generates the potential difference across the terminals of the cell, even when no current is drawn from it. When the cell is connected to a conducting circuit element, the potential difference sets the charges in motion in the conductor and produces an electric current. In order to maintain the current in a given electric circuit, the cell has to expend its chemical energy stored in it. We define the electric potential difference between 2 points in an electric circuit carrying some current as the work done to move a unit charge from one point to the other. Potential difference V between 2 points equals work done, W, charge Q. The SI unit of electric potential difference is volt, V, named after Alessandro Volta, 1745-1827, an Italian physicist. 1 volt is the potential difference between 2 points in a current carrying conductor when 1 joule of work is done to move a charge of 1 coulomb from one point to the other. The potential difference is measured by means of an instrument called the voltmeter. The voltmeter is always connected in parallel across the points between which the potential difference is to be measured. Example 12.2. How much work is done in moving a charge of 2C across 2 points having a potential difference 12 volts? Solution. The amount of charge Q that flows between 2 points of potential difference V equals 12 volts is 2C. Thus, the amount of work W done in moving the charge from EQ. 12.2 is W equals VQ equals 12 volts times 2C equals 24J. Questions. 1. Name a device that helps to maintain a potential difference across a conductor. 2. What is meant by saying that the potential difference between 2 points is 1 volt? 3. How much energy is given to each coulomb of charge passing through a 6 volts battery? 12.3 Circuit diagram. We know that an electric circuit, as shown in figure 12.1, comprises a cell or a battery, a plug key, electrical components, and connecting wires. It is often convenient to draw a schematic diagram in which different components of the circuit are represented by the symbols conveniently used. Conventional symbols used to represent some of the most commonly used electrical components are given in table 12.1. Table 12.1 symbols of some commonly used components in circuit diagrams. 12.4 Ohm's law. Is there a relationship between the potential difference across a conductor and the current through it? Let us explore with an activity. Activity 12.1. Set up a circuit as shown in figure 12.2, consisting of a nichrome wire XY of length, say 0.5 meters, an ammeter, a voltmeter, and 4 cells of 1.5 volts each. Nichrome is an alloy of nickel, chromium, manganese, and iron metals. Figure 12.2 Electric circuit for studying Ohm's law. First, use only one cell as the source in the circuit. Note the reading in the ammeter I for the current and reading of the voltmeter V for the potential difference across the nichrome wire XY in the circuit. Tabulate them in the table given. Next, connect 2 cells in the circuit and note the respective readings of the ammeter and voltmeter for the values of current through the nichrome wire and potential difference across the nichrome wire. Repeat the above steps using 3 cells and then 4 cells in the circuit separately. Calculate the ratio of V to I for each pair of potential difference V and current I. S. No. Number of cells used in the circuit. Current through the nichrome wire I ampere. Potential difference across the nichrome wire V volt. V I volt ampere. 1, 1, 2, 2, 3, 3, 4, 4. Plot a graph between V and I and observe the nature of the graph. In this activity, you will find that approximately the same value for VI is obtained in each case. Thus the VI graph is a straight line that passes through the origin of the graph, as shown in figure 12.3. Thus VI is a constant ratio. Figure 12.3 VI graph for a nichrome wire. A straight line plot shows that as the current through a wire increases, the potential difference across the wire increases linearly. This is Ohm's law. In 1827, a German physicist Georg Simon Ohm, 1787-1854, found out the relationship between the current I flowing in a metallic wire and the potential difference across its terminals. The potential difference V across the ends of a given metallic wire in an electric circuit is directly proportional to the current flowing through it, provided its temperature remains the same. This is called Ohm's law. In other words, in EQ, 12.4 R is a constant for the given metallic wire at a given temperature and is called its resistance. It is the property of a conductor to resist the flow of charges through it. Its SI unit is Ohm, represented by the Greek letter omega. According to Ohm's law, if the potential difference across the two ends of a conductor is 1 volt and the current through it is 1A, then the resistance R of the conductor is 1 ohm. That is, also from EQ, 12.5 we get I equals V R 12.7. It is obvious from EQ, 12.7 that the current through a resistor is inversely proportional to its resistance. If the resistance is doubled, the current gets halved. In many practical cases, it is necessary to increase or decrease the current in an electric circuit. A component used to regulate current without changing the voltage source is called variable resistance. In an electric circuit, a device called rheostat is often used to change the resistance in the circuit. We will now study about electrical resistance of a conductor with the help of following activity. Activity 12.2. Take a nichrome wire, a torch bulb, a 10W bulb and an ammeter, 0 to 5 arranged, a plug key and some connecting wires. Set up the circuit by connecting 4 dry cells of 1.5 volts each in series with the ammeter leaving a gap XY in the circuit, as shown in figure 12.4. Figure 12.4. Complete the circuit by connecting the nichrome wire in the gap XY. Plug the key. Note down the ammeter reading. Take out the key from the plug. Note, always take out the key from the plug after measuring the current through the circuit. Replace the nichrome wire with the torch bulb in the circuit and find the current through it by measuring the reading of the ammeter. Now repeat the above step with the 10W bulb in the gap XY. Are the ammeter readings different for different components connected in the gap XY? What do the above observations indicate? You may repeat this activity by keeping any material component in the gap. Observe the ammeter readings in each case. Analyze the observations. In this activity, we observe that the current is different for different components. Why do they differ? Certain components offer an easy path for the flow of electric current while the others resist the flow. We know that motion of electrons in an electric circuit constitutes an electric current. The electrons, however, are not completely free to move within a conductor. They are restrained by the attraction of the atoms among which they move. Thus, motion of electrons through a conductor is retarded by its resistance. A component of a given size that offers a low resistance is a good conductor. A conductor having some appreciable resistance is called a resistor. A component of identical size that offers a high resistance is a poor conductor. An insulator of the same size offers even higher resistance. 12.5 factors on which the resistance of a conductor depends. Activity 12.3. Complete an electric circuit consisting of a cell, an ammeter, a nichrome wire of length L, say, marked 1, and a plug key, as shown in figure 12.5. Figure 12.5 electric circuit to study the factors on which the resistance of conducting wires depends. Now, plug the key. Note the current in the ammeter. Replace the nichrome wire by another nichrome wire of same thickness but twice the length, that is 2L, marked 2, in the figure 12.5. Note the ammeter reading. Now replace the wire by a thicker nichrome wire of the same length L, marked 3. A thicker wire has a larger cross-sectional area. Again, note down the current through the circuit. Instead of taking a nichrome wire, connect a copper wire, marked 4, in figure 12.5 in the circuit. Let the wire be of the same length and same area of cross-section as that of the first nichrome wire, marked 1. Note the value of the current. Notice the difference in the current in all cases. Does the current depend on the length of the conductor? Does the current depend on the area of cross-section of the wire used? It is observed that the ammeter reading decreases to 1/2 when the length of the wire is doubled. The ammeter reading is increased when a thicker wire of the same material and of the same length is used in the circuit. A change in ammeter reading is observed when a wire of different material of the same length and the same area of cross-section is used. On applying Ohm's law, EQs. 12.5, 12.7, we observe that the resistance of the conductor depends I on its length, E on its area of cross-section, and E on the nature of its material. Precise measurements have shown the resistance of a uniform metallic conductor is directly proportional to its length L and inversely proportional to the area of cross-section A. That is, combining EQs, 12.8 and 12.9 we get where rho is a constant of proportionality and is called the electrical resistivity of the material of the conductor. The SI unit of resistivity is omega m. It is a characteristic property of the material. The metals and alloys have very low resistivity in the range of 10-8 ohms m to 10-6 ohms m. They are good conductors of electricity. Insulators like rubber and glass have resistivity of the order of 1012 to 1017 ohms m. Both the resistance and resistivity of a material vary with temperature. Table 12.2 reveals that the resistivity of an alloy is generally higher than that of its constituent metals. Alloys do not oxidize, burn readily at high temperatures. For this reason, they are commonly used in electrical heating devices like electric iron, toasters, etc. Tungsten is used almost exclusively for filaments of electric bulbs, whereas copper and aluminium are generally used for electrical transmission lines. Table 12.2 electrical resistivity asterisk of some substances at 20 degrees Celsius. Example 12.3. Of how much current will an electric bulb draw from a 220 volt source if the resistance of the bulb filament is 1200 ohms? B. How much current will an electric heater coil draw from a 220 volt source if the resistance of the heater coil is 100 ohms? Solution. We are given V equals 220 volts, R equals 1200 ohms. From EQ. 12.6 we have the current I equals 220 volts, 1200 ohms equals 0.18A. B. We are given V equals 220 volts, R equals 100 ohms. From EQ. 12.6 we have the current I equals 220 volts, 100 ohms equals 2.2A. Note the difference of current drawn by an electric bulb and electric heater from the same 220 volt source. Example 12.4. The potential difference between the terminals of an electric heater is 60 volts when it draws a current of 4 from the source. What current will the heater draw if the potential difference is increased to 120 volts? Solution. We are given potential difference V equals 60 volts, current I equals 4A. According to Ohm's law, when the potential difference is increased to 120 volts, the current is given by current equals the current through the heater becomes 8A. Example 12.5. Resistance of a metal wire of length 1 meter is 26 ohms at 20 degrees Celsius. If the diameter of the wire is 0.3 millimeters, what will be the resistivity of the metal at that temperature? Using table 12.2, predict the material of the wire. Solution. We are given the resistance R of the wire equals 26 ohms, the diameter D equals 0.3 millimeters equals 3 times 10 to 4 m, and the length L of the wire equals 1 meter. Therefore, from EQ, 12.10, the resistivity of the given metallic wire is rho equals Ra, L equals R pi D2, 4L. Substitution of values in this gives rho equals 1.84 times 10 minus 6 ohms m. The resistivity of the metal at 20 degrees Celsius is 1.84 times 10 minus 6 ohms m. From table 12.2, we see that this is the resistivity of manganese. Example 12.6. A wire of given material having length L and area of cross-section A has a resistance of 4 ohms. What would be the resistance of another wire of the same material having length L2 and area of cross-section 2A? Solution. For first wire, R1 equals rho equals 4 ohms. Now for second wire, R2. R2 R1. R2 equals 1 ohm. The resistance of the new wire is 1 ohm. Questions. 1. On what factors does the resistance of a conductor depend? 2. Will current flow more easily through a thick wire or a thin wire of the same material when connected to the same source? Why? 3. Let the resistance of an electrical component remains constant while the potential difference across the two ends of the component decreases to half of its former value. What change will occur in the current through it? 4. Why coils of electric toasters and electric irons made of an alloy rather than a pure metal? 5. Use the data in table 12.2 to answer the following. Of which among iron and mercury is a better conductor? B. Which material is the best conductor? 12.6 Resistance of a system of resistors. In preceding sections, we learned about some simple electric circuits. We have noticed how the current through a conductor depends upon its resistance and the potential difference across its ends. In various electrical gadgets, we often use resistors in various combinations. We now therefore intend to see how Ohm's law can be applied to combinations of resistors. There are two methods of joining the resistors together. Figure 12.6 shows an electric circuit in which three resistors having resistances R1, R2, and R3, respectively, are joined end to end. Here the resistors are said to be connected in series. Figure 12.6 resistors in series. Figure 12.7 shows a combination of resistors in which three resistors are connected together between points X and Y. Here the resistors are said to be connected in parallel. Figure 12.7 resistors in parallel. 12.6.1 resistors in series. What happens to the value of current when a number of resistors are connected in series in a circuit? What would be their equivalent resistance? Let us try to understand these with the help of the following activities. Activity 12.4. Join three resistors of different values in series. Connect them with a battery, an ammeter, and a plug key, as shown in figure 12.6. You may use the resistors of values like 1 ohm, 2 ohms, 3 ohms, etc., and a battery of 6 volts for performing this activity. Plug the key. Note the ammeter reading. Change the position of ammeter to anywhere in between the resistors. Note the ammeter reading each time. Do you find any change in the value of current through the ammeter? You will observe that the value of the current in the ammeter is the same, independent of its position in the electric circuit. It means that in a series combination of resistors, the current is the same in every part of the circuit or the same current through each resistor. Activity 12.5. In activity 12.4, insert a voltmeter across the ends X and Y of the series combination of three resistors, as shown in figure 12.6. Plug the key in the circuit and note the voltmeter reading. It gives the potential difference across the series combination of resistors. Let it be V. Now measure the potential difference across the two terminals of the battery. Compare the two values. Take out the plug key and disconnect the voltmeter. Now insert the voltmeter across the ends X and P of the first resistor, as shown in figure 12.8. Figure 12.8. Plug the key and measure the potential difference across the first resistor. Let it be V1. Similarly, measure the potential difference across the other two resistors separately. Let these values be V2 and V3, respectively. Deduce a relationship between V1, V2, and V3. You will observe that the potential difference V is equal to the sum of potential differences V1, V2, and V3. That is, the total potential difference across a combination of resistors in series is equal to the sum of potential difference across the individual resistors. That is, V equals V1 plus V2 plus V3, 12.11. In the electric circuit shown in figure 12.8, let I be the current through the circuit. The current through each resistor is also I. It is possible to replace the three resistors joined in series by an equivalent single resistor of resistance R, such that the potential difference V across it and the current I through the circuit remains the same. Applying the Ohm's law to the entire circuit, we have V equals IR 12.12. On applying Ohm's law to the three resistors separately, we further have V1 equals IR1 12.13 A. V2 equals IR2 12.13 B. And V3 equals IR3 12.13 C. From EQ 12.11. IR equals IR1 plus IR2 plus IR3. Or RS equals R1 plus R2 plus R3 12.14. We can conclude that when several resistors are joined in series, the resistance of the combination Rs equals the sum of their individual resistances R1, R2, R3, and is thus greater than any individual resistance. Example 12.7. An electric lamp whose resistance is 20 ohms and a conductor of 4 ohms resistance are connected to a 6 volts battery, figure 12.9. Calculate at the total resistance of the circuit B, the current through the circuit, and C, the potential difference across the electric lamp and conductor. Figure 12.9. An electric lamp connected in series with a resistor of 4 ohms to a 6 volts battery. Solution. The resistance of electric lamp R1 equals 20 ohms. The resistance of the conductor connected in series R2 equals 4 ohms. Then the total resistance in the circuit. R equals R1 plus R2. RS equals 20 ohms plus 4 ohms equals 24 ohms. The total potential difference across the two terminals of the battery V equals 6V. Now by Ohm's law, the current through the circuit is given by I equals V RS equals 6 volts 24 ohms equals 0.25 A. Applying Ohm's law to the electric lamp and conductor separately, we get potential difference across the electric lamp. V1 equals 20 ohms times 0.25 A equals 5 volts, and that across the conductor, V2 equals 4 ohms times 0.25 A equals 1V. Suppose that we like to replace the series combination of electric lamp and conductor by a single and equivalent resistor. Its resistance must be such that a potential difference of 6 volts across the battery terminals will cause a current of 0.25 A in the circuit. The resistance R of this equivalent resistor would be R equals VI equals 6 volts 0.25 A equals 24 ohms. This is the total resistance of the series circuit. It is equal to the sum of the two resistances. Questions. 1. Draw a schematic diagram of a circuit consisting of a battery of 3 cells of 2 volts each, a 5 ohms resistor, an 8 ohms resistor, and a 12 ohms resistor, and a plug key, all connected in series. 2. Redraw the circuit of question 1, putting in an ammeter to measure the current through the resistors and a voltmeter to measure the potential difference across the 12 ohms resistor. What would be the readings in the ammeter and the voltmeter? 12.6.2 resistors in parallel. Now, let us consider the arrangement of 3 resistors joined in parallel with a combination of cells or a battery, as shown in fig. 1.2.7. Activity 12.6. Make a parallel combination, XY, of 3 resistors having resistances R1, R2, and R3, respectively. Connect it with a battery, a plug key, and an ammeter, as shown in figure 12.10. Also connect a voltmeter in parallel with the combination of resistors. Figure 12.10. Plug the key and note the ammeter reading. Let the current be I. Also take the voltmeter reading. It gives the potential difference V across the combination. The potential difference across each resistor is also V. This can be checked by connecting the voltmeter across each individual resistor. See figure 12.11. Figure 12.11. Take out the plug from the key. Remove the ammeter and voltmeter from the circuit. Insert the ammeter in series with the resistor R1, as shown in figure 12.11. Note the ammeter reading, I1. Similarly, measure the currents through R2 and R3. Let these be I2 and I3, respectively. What is the relationship between I1, I2, and I3? It is observed that the total current I is equal to the sum of the separate currents through each branch of the combination. I equals I1 plus I2 plus I3, 12.15. Let RP be the equivalent resistance of the parallel combination of resistors. By applying Ohm's law to the parallel combination of resistors, we have I equals V RP, 12.16. On applying Ohm's law to each resistor, we have I1 equals V R1, I2 equals V R2, and I3 equals V R3, 12.17. From EQs, 12.15 to 12.17, we have V RP equals V R1 plus V R2 plus V R3. Or 1 RP equals 1 R1 plus 1 R2 plus 1 R3, 12.18. Thus, we may conclude that the reciprocal of the equivalent resistance of a group of resistances joined in parallel is equal to the sum of the reciprocals of the individual resistances. Example 12.8. In the circuit diagram given in figure 12.10, suppose the resistors R1, R2 and R3 have the values 5 ohms, 10 ohms, 30 ohms, respectively, which have been connected to a battery of 12V. Calculate the current through each resistor, B, the total current in the circuit, and C, the total circuit resistance. Solution. R1 equals 5 ohms, R2 equals 10 ohms, and R3 equals 30 ohms. Potential difference across the battery, V equals 12V. This is also the potential difference across each of the individual resistor, therefore, to calculate the current in the resistors, we use Ohm's law. The current I1 through R1 equals V, R1. I1 equals 12 volts, 5 ohms equals 2.4A. The current I2 through R2 equals V, R2. I2 equals 12 volts, 10 ohms equals 1.2A. The current I3 through R3 equals V, R3. I3 equals 12 volts, 30 ohms equals 0.4A. The total current in the circuit, I equals I1 plus I2 plus I3, equals 2.4 plus 1.2 plus 0.4, equals 4. The total resistance RP is given by EQ, 12.18. Thus, RP equals 3 ohms. Example 12.9. If in figure 12.12, R1 equals 10 ohms, R2 equals 40 ohms, R3 equals 30 ohms, R4 equals 20 ohms, R5 equals 60 ohms, and a 12 volts battery is connected to the arrangement. Calculate the total resistance in the circuit and B, the total current flowing in the circuit. Figure 12.12, an electric circuit showing the combination of series and parallel resistors. Solution. Suppose we replace the parallel resistors R1 and R2 by an equivalent resistor of resistance R. Similarly, we replace the parallel resistors R3, R4, and R5 by an equivalent single resistor of resistance R. Then using EQ, 12.18, we have 1 R equals 1/10 plus 1/40 equals 5/40, that is R equals 8 ohms. Similarly, 1 R equals 1/30 plus 1/20 plus 1/60 equals 6/60. That is R equals 10 ohms. Thus, the total resistance R equals R plus R equals 18 ohms. To calculate the current, we use Ohm's law and get I equals V, R equals 12 volts, 18 ohms equals 0.67A. We have seen that in a series circuit the current is constant throughout the electric circuit. Thus, it is obviously impractical to connect an electric bulb and an electric heater in series because they need currents of widely different values to operate properly. See example 12.3. Another major disadvantage of a series circuit is that when one component fails, the circuit is broken and none of the components works. If you have used fairy lights to decorate buildings on festivals, on marriage celebrations, etc., you might have seen the electrician spending a lot of time in trouble locating and replacing the dead bulb. Each has to be tested to find which has fused or gone. On the other hand, a parallel circuit divides the current through the electrical gadgets. The total resistance in a parallel circuit is decreased as 3Q. 12.18. This is helpful particularly when each gadget has different resistance and requires different current to operate properly. Questions. 1. Judge the equivalent resistance when the following are connected in parallel at 1 ohm and 106 ohms, B, 1 ohm and 103 ohms and 106 ohms. 2. An electric lamp of 100 ohms, a toaster of resistance 50 ohms, and a water filter of resistance 500 ohms are connected in parallel to a 220 volt source. What is the resistance of an electric iron connected to the same source that takes as much current as all three appliances, and what is the current through it? 3. What are the advantages of connecting electrical devices in parallel with the battery instead of connecting them in series? 4. How can three resistors of resistances 2 ohms, 3 ohms, and 6 ohms be connected to give a total resistance of 4 ohms, B, 1 ohm? 5. What is, at the highest B, the lowest total resistance that can be secured by combinations of 4 coils of resistance 4 ohms, 8 ohms, 12 ohms, 24 ohms? 12.7 Heating effect of electric current. We know that a battery or a cell is a source of electrical energy. The chemical reaction within the cell generates the potential difference between its two terminals that sets the electrons in motion to flow the current through a resistor or a system of resistors connected to the battery. We have also seen, in section 12.2, that to maintain the current, the source has to keep expending its energy. Where does this energy go? A part of the source energy in maintaining the current may be consumed into useful work, like in rotating the blades of an electric fan. Rest of the source energy may be expended in heat to raise the temperature of gadget. We often observe this in our everyday life. For example, an electric fan becomes warm if used continuously for longer time, etc. On the other hand, if the electric circuit is purely resistive, that is, a configuration of resistors only connected to a battery, the source energy continually gets dissipated entirely in the form of heat. This is known as the heating effect of electric current. This effect is utilized in devices such as electric heater, electric iron, etc. Consider a current I flowing through a resistor of resistance R. Let the potential difference across it be figure 12.13. Let T be the time during which a charge Q flows across. The work done in moving the charge Q through a potential difference V is VQ. Therefore, the source must supply energy equal to VQ in time T. Hence the power input to the circuit by the source is. Or the energy supplied to the circuit by the source in time T is P times T, that is V. What happens to this energy expended by the source? This energy gets dissipated in the resistor as heat. Thus for a steady current I, the amount of heat H produced in time T is H equals V, 12.20. Applying Ohm's law, EQ. 12.5 we get H equals I2 RT, 12.21. This is known as Joule's law of heating. The law implies that heat produced in a resistor is I directly proportional to the square of current for a given resistance, E directly proportional to resistance for a given current, and E directly proportional to the time for which the current flows through the resistor. In practical situations, when an electric appliance is connected to a known voltage source, EQ. 12.21 is used after calculating the current through it using the relation I equals VR. Figure 12.13, a steady current in a purely resistive electric circuit. Example 12.10. An electric iron consumes energy at a rate of 840 W when heating is at the maximum rate and 360 W when the heating is at the minimum. The voltage is 220 V. What are the current and the resistance in each case? Solution. From EQ. 12.19, we know that the power input is P equals VI. Thus the current I equals PV. When heating is at the maximum rate, I equals 840 with 220 volts equals 3.82 A. And the resistance of the electric iron is R equals V, I equals 220 volts, 3.82 A equals 57.60 ohms. B. When heating is at the minimum rate, I equals 360 with 220 volts equals 1.64 A. And the resistance of the electric iron is R equals V, I equals 220 volts, 1.64 equals 134.15 ohms. Example 12.11. 100 J of heat is produced each second in a 4 ohms resistance. Find the potential difference across the resistor. Solution. H equals 100 J, R equals 4 ohms, T equals 1 S, V equals. From EQ. 12.21, we have the current through the resistors. I equals square root H, RT. Equals square root 100 J, 4 ohms times 1 S. Equals 5 A. Thus the potential difference across the resistor, V from EQ. 12.5 is V equals IR. Equals 5 A times 4 ohms. Equals 20 V. Questions. 1. Why does the cord of an electric heater not blow while the heating element does? 2. Compute the heat generated while transferring 96,000 coulomb of charge in 1 hour through a potential difference of 50 V. 3. An electric iron of resistance 20 ohms takes a current of 5 A. Calculate the heat developed in 30 S. 12.7.1 Practical applications of heating effect of electric current. The generation of heat in a conductor is an inevitable consequence of electric current. In many cases, it is undesirable as it converts useful electrical energy into heat. In electric circuits, the unavoidable heating can increase the temperature of the components and alter the properties. However, heating effect of electric current has many useful applications. The electric laundry iron, electric toaster, electric oven, electric kettle, and electric heater are some of the familiar devices based on Joule's heating. The electric heating is also used to produce light, as in an electric bulb. Here, the filament must retain as much of the heat generated as is possible, so that it gets very hot and emits light. It must not melt at such high temperature. A strong metal with high melting points such as tungsten, melting point 3380 degrees Celsius, is used for making bulb filaments. The filament should be thermally isolated as much as possible, using insulating support, etc. The bulbs are usually filled with chemically inactive nitrogen and argon gases to prolong the life of filament. Most of the power consumed by the filament appears as heat, but a small part of it is in the form of light radiated. Another common application of Joule's heating is the fuse used in electric circuits. It protects circuits and appliances by stopping the flow of any unduly high electric current. The fuse is placed in series with the device. It consists of a piece of wire made of a metal or an alloy of appropriate melting point, for example aluminium, copper, iron, lead, etc. If a current larger than the specified value flows through the circuit, the temperature of the fuse wire increases. This melts the fuse wire and breaks the circuit. The fuse wire is usually encased in a cartridge of porcelain or similar material with metal ends. The fuses used for domestic purposes are rated as 1A, 2A, 3A, 5A, 10A, etc. For an electric iron which consumes 1 kilowatt electric power when operated at 220 volts, a current of 1220 A, that is 4.54, will flow in the circuit. In this case, a fiber fuse must be used. 12.8 electric power. You have studied in your earlier class that the rate of doing work is power. This is also the rate of consumption of energy. Equation 12.21 gives the rate at which electric energy is dissipated or consumed in an electric circuit. This is also termed as electric power. The power P is given by P equals by, or P equals I2 R equals V2 R 12.22. The SI unit of electric power is Watt W. It is the power consumed by a device that carries 1 current when operated at a potential difference of 1V. Thus, 1 W equals 1 volt times 1 ampere equals 1 volt A 12.23. The unit watt is very small. Therefore, in actual practice we use a much larger unit called kilowatt. It is equal to 1000 watts. Since electrical energy is the product of power and time, the unit of electric energy is therefore watt-hour WH. 1 watt-hour is the energy consumed when 1 watt of power is used for 1 hour. The commercial unit of electric energy is kilowatt-hour kWh, commonly known as unit. 1 kilowatt H equals 1000 watt times 3600 second. Equals 3.6 times 106 watt second. Equals 3.6 times 106 joule J. More to know, many people think that electrons are consumed in an electric circuit. This is wrong. We pay the electricity board or electric company to provide energy to move electrons through the electric gadgets like electric bulb, fan, and engines. We pay for the energy that we use. Example 12.12. An electric bulb is connected to a 220 volts generator. The current is 0.50 A. What is the power of the bulb? Solution. P equals by equals 220 volts times 0.50 A equals 110 J S equals 110 W. Example 12.13. An electric refrigerator rated 400 W operates 8 hours per day. What is the cost of the energy to operate it for 30 days at 3 rupees per kilowatt H? Solution. The total energy consumed by the refrigerator in 30 days would be 400 W times 8.0 hour per day times 30 days equals 96,000 WH equals 96 kilowatts H. Thus the cost of energy to operate the refrigerator for 30 days is 96 kilowatts H times 3 rupees per kilowatt H equals 288 rupees. Questions. 1. What determines the rate at which energy is delivered by a current? 2. An electric motor takes fiber from a 220 volts line. Determine the power of the motor and the energy consumed in 2H. What you have learned. A stream of electrons moving through a conductor constitutes an electric current. Conventionally, the direction of current is taken opposite to the direction of flow of electrons. The SI unit of electric current is ampere. To set the electrons in motion in an electric circuit, we use a cell or a battery. A cell generates a potential difference across its terminals. It is measured in volts V. Resistance is a property that resists the flow of electrons in a conductor. It controls the magnitude of the current. The SI unit of resistance is ohm, omega. Ohm's law, the potential difference across the ends of a resistor is directly proportional to the current through it provided its temperature remains the same. The resistance of a conductor depends directly on its length, inversely on its area of cross-section, and also on the material of the conductor. The equivalent resistance of several resistors in series is equal to the sum of their individual resistances. A set of resistors connected in parallel has an equivalent resistance Rp given by. The electrical energy dissipated in a resistor is given by W equals V times I times T. The unit of power is Watt W. 1 watt of power is consumed when 1 of current flows at a potential difference of 1V. The commercial unit of electrical energy is kilowatt-hour kWh. 1 kilowatt H equals 3,600,000 J equals 3.6 times 106 J. Exercises. 1. A piece of wire of resistance R is cut into 5 equal parts. These parts are then connected in parallel. If the equivalent resistance of this combination is R, then the ratio R is 1/25 B, 1/5 C, 5 D, 25. 2. Which of the following terms does not represent electrical power in a circuit? I2R, B, IR2, C, Vi, D, V2R. 3. An electric bulb is rated 220 volts and 100 W. When it is operated on 110 volts, the power consumed will be at 100 W, B, 75 W, C, 50 W, D, 25 W. 4. Two conducting wires of the same material and of equal lengths and equal diameters are first connected in series and then parallel in a circuit across the same potential difference. The ratio of heat produced in series and parallel combinations would be 1, 2, B, 2, 1, C, 1, 4, D, 4, 1. 5. How is a voltmeter connected in a circuit to measure the potential difference between 2 points? 6. A copper wire has diameter 0.5 millimeters and resistivity of 1.6 times 10 minus 8 ohms m. What will be the length of this wire to make its resistance 10 ohms? How much does the resistance change if the diameter is doubled? 7. The values of current I flowing in a given resistor for the corresponding values of potential difference V across the resistor are given below. I. Amperes. 0.5. 1.0. 2.0. 3.0. 4.0. B. Volts. 1.6. 3.4. 6.7. 10.2. 13.2. Plot a graph between V and I and calculate the resistance of that resistor. 8. When a 12 volts battery is connected across an unknown resistor, there is a current of 2.5 milliamperes in the circuit. Find the value of the resistance of the resistor. 9. A battery of 9 volts is connected in series with resistors of 0.2 ohms, 0.3 ohms, 0.4 ohms, 0.5 ohms, and 12 ohms respectively. How much current would flow through the 12 ohms resistor? 10. How many 176 ohms resistors in parallel are required to carry fiber on a 220 volts line? 11. Show how you would connect 3 resistors, each of resistance 6 ohms, so that the combination has a resistance of I, 9 ohms, E, 4 ohms. 12. Several electric bulbs designed to be used on a 220 volts electric supply line are rated 10 W. How many lamps can be connected in parallel with each other across the 2 wires of 220 volts line if the maximum allowable current is fiber? 13. A hot plate of an electric oven connected to a 220 volts line has 2 resistance coils A and B, each of 24 ohms resistance, which may be used separately, in series, or in parallel. What are the currents in the 3 cases? 14. Compare the power used in a 2 ohms resistor in each of the following circuits: I, a 6 volts battery in series with 1 ohm and 2 ohms resistors, and E, a 4 volts battery in parallel with 12 ohms and 2 ohms resistors. 15. Two lamps, one rated 100W at 220 volts and the other 60W at 220 volts, are connected in parallel to electric mains supply. What current is drawn from the line if the supply voltage is 220 volts? 16. Which uses more energy, a 250W TV set in 1 hour or a 1200W toaster in 10 minutes? 17. An electric heater of resistance 8 ohms draws 15 from the service mains 2 hours. Calculate the rate at which heat is developed in the heater. 18. Explain the following. Why is the tungsten used almost exclusively for filament of electric lamps? B. Why are the conductors of electric heating devices, such as bread toasters and electric irons, made of an alloy rather than a pure metal? C. Why is the series arrangement not used for domestic circuits? D. How does the resistance of a wire vary with its area of cross-section? E. Why are copper and aluminium wires usually employed for electricity transmission?